There are roughly 2 trillion galaxies in the observable universe. Each one contains hundreds of billions of stars. Around those stars orbit trillions upon trillions of planets. The numbers are so enormous that the conclusion seems obvious. Life must be everywhere. Intelligence must be common. The cosmos must be buzzing with civilizations building, exploring, communicating. But what if every single assumption buried inside that logic is wrong? What if the universe is not a garden waiting to bloom, but a desert where the conditions for anything beyond a microbe are so absurdly specific, so laughably unlikely, built not on speculation but on planetary science, evolutionary biology, and astrophysics, that says exactly this? It is called the rare Earth hypothesis. And its most disturbing consequence is not that aliens are hiding. It is not that they are dangerous. It is something far lonelier. It is the possibility that we are it. That in a cosmos of unimaginable scale, the silence is not a mystery. It is an answer. Imagine you win the lottery. Not a small one, the big one. The kind where the odds are 1 in 300 million. You hold the ticket. The numbers match. You scream. You cry. You tell yourself you are the luckiest person alive. Now imagine someone walks up to you and says that winning that lottery was not enough. To actually collect the money, you also needed to have been born on a Tuesday, in a leap year, during a solar eclipse, in a hospital located within 5 kilometers of a river that flows north, on a continent that has exactly 3 active volcanoes, on a planet orbiting a star that has not flickered in 4 billion years. And every single one of those conditions had to be true simultaneously. Not one of them could be missing. Not one could be slightly off. Miss a single requirement by even a fraction, and the ticket is worthless. You would no longer feel lucky. You would feel something closer to terror. Because you would realize that the odds of everything lining up were so unimaginably small that your existence on the winner's podium is not a triumph. It is a statistical anomaly so extreme it borders on the absurd. That feeling, that vertigo between wonder and dread, is the emotional core of the rare Earth hypothesis. And it is exactly what a growing number of scientists believe describes our situation in the universe. The rare Earth hypothesis is not a piece of science fiction. It is not a thought experiment designed to make you feel small at a dinner party. It is a formal scientific argument, rooted in decades of research across planetary science, evolutionary biology, geology, and astrophysics, and it makes a claim that is as simple as it is devastating. Complex life, the kind that builds eyes and brains and radio telescopes, the kind that writes music and argues about politics and wonders whether it is alone, may be so extraordinarily rare in the universe that for all practical purposes, it might as well not exist anywhere else. Not rare in the way that a 4-leaf clover is rare, where if you walk through enough fields, you will eventually find one. Rare in the way that a specific arrangement of atoms is rare. Rare in the way that demands so many independent conditions to align simultaneously that the probability collapses towards 0 even across a cosmos containing trillions of planets. The idea was formalized in the year 2000 by paleontologist Peter Ward and astronomer Donald Brownlee, both from the University of Washington. They published a book titled Rare Earth, and it landed like a grenade in the scientific community. For decades, the prevailing mood in astrobiology had been optimistic. The Drake equation, that famous formula designed to estimate the number of communicative civilizations in the galaxy, had been wielded like a torch of hope. Plug in reasonable numbers, and you get thousands of civilizations, maybe millions. The galaxy should be a crowded neighborhood. The universe should be a party. Ward and Brownlee looked at the same galaxy and saw a graveyard. Not because they were pessimists, but because they did something that the optimists had been quietly avoiding. They looked at Earth not as a typical planet, but as a crime scene. They catalogued every single condition that had to be true for complex life to arise here, not just one or two big ones, all of them. The type of star, the position in the galaxy, the chemical composition of the planet, the presence of water, the behavior of the magnetic field, the existence of plate tectonics, the size of the moon, the arrangement of neighboring gas giants, the frequency of mass extinctions, the stability of the climate over billions of years, the specific sequence of evolutionary accidents that turned simple chemistry into thinking, feeling, conscious organisms. And when they multiplied these probabilities together, the number did not just shrink, it evaporated. Now, this is where the distinction becomes critical, and it is a distinction that most casual conversations about alien life completely ignore. The rare Earth hypothesis does not say that life itself is rare. That is a very different claim. Simple life, microbial life, the kind of single-celled organisms that dominated Earth for roughly 3 billion years, may actually be common. There is growing evidence to support this. Life appeared on Earth astonishingly fast. The planet formed around 4.5 billion years ago. The surface was molten. It was being bombarded by asteroids. It was a hellscape. And yet, within just a few 100 million years after conditions became even marginally tolerable, microbial life was already there. Fossil evidence of ancient microorganisms dates back to at least 3.5 billion years ago, and chemical signatures suggest biological activity possibly even earlier. That speed is significant. It suggests that the jump from chemistry to biology, from organic molecules to self-replicating cells, might not be the hard part. Given the right ingredients, liquid water, carbon-based chemistry, an energy source, simple life might emerge almost inevitably. It might be popping up on rocky worlds across the galaxy right now, buried in subsurface oceans, clinging to hydrothermal vents, drifting through the atmospheres of worlds we have not yet named. But here is the knife twist. Simple life is not complex life. A bacterium is not a brain. A colony of microbes on a wet rock is not a civilization, and the distance between those two things is not a gentle slope. It is a cliff face. It is a wall so high and so sheer that in 4 billion years of Earth's history, the climb was made only once, through a chain of events so specific and so improbable that reproducing it on another world may require conditions that almost never exist. The rare Earth hypothesis draws a hard line between the emergence of microbial life and the emergence of complex multicellular organisms capable of developing intelligence and technology. It argues that the first event might be common, maybe even trivially easy on a cosmic scale. But the second event, the one that produces creatures like us, requires the universe to thread a needle so fine that the odds become astronomical in the most literal sense of the word. This is where the disturbing consequence begins to take shape, and it is important to define it precisely because it is not what most people expect. The disturbing consequence of the rare Earth hypothesis is not a doomsday scenario. It is not a prediction that aliens will invade, or that a cosmic catastrophe is heading our way, or that humanity is doomed to extinction by some universal law. The disturbing consequence is something quieter, colder, and in many ways worse. It is the possibility that we are alone, not alone in the poetic sense, where you feel lonely staring up at the night sky. Alone in the mathematical sense. Alone in the sense that the nearest technological civilization, if one exists at all, may be so far away in space and so separated from us in time that no signal, no probe, no act of communication could ever bridge the gap. Alone in the sense that the universe could contain 100 billion galaxies, each with 100 billion stars, each with a handful of planets, and not a single one of them, not one, harbors anything more complex than a film of algae on a warm rock. That is the weight of this idea. It is not the horror of encountering something dangerous out there. It is the horror of realizing there might be nothing out there at all. Nothing that thinks, nothing that wonders, nothing that builds or dreams or asks questions about its own existence. Just an endless expanse of physics and chemistry grinding away in the dark, producing stars and galaxies and planets in staggering abundance, but almost never producing a mind. Think about what that means for a moment. We grow up in a culture saturated with the assumption that contact is inevitable. Science fiction has trained us to expect it. Every movie, every television show, every novel that features aliens operates on the unspoken premise that the universe is populated. We imagine first contact as a milestone, a dramatic turning point in human history where we meet our cosmic neighbors and everything changes. The search for extraterrestrial intelligence, SETI, has been listening for signals since the 1960s. We have sent messages. We have launched golden records into the void. We have aimed radio telescopes at thousands of stars, straining to hear even a whisper, and the silence has been total, absolute, unbroken. The rare Earth hypothesis says that this silence is not a technological failure. It is not because our instruments are too weak or our search is too young. The silence is the data, the emptiness is the answer. And the answer is that the universe is not ignoring us, it simply has no one else to send. Now, it would be easy to wave this away. It would be easy to say that the rare Earth hypothesis is just one idea among many, that it is speculative, that it relies on assumptions we cannot verify. And to some extent, that is true. We have a sample size of exactly one planet with complex life. Drawing universal conclusions from a single example is always dangerous. But the strength of the rare Earth argument does not come from certainty. It comes from the structure of the reasoning. It does not claim to prove that we are alone. It claims something more subtle and more powerful. It says that when you honestly assess the chain of conditions required for complex life, and when you honestly assess the probability of each link in that chain, the resulting number is so small that the burden of proof shifts. The question is no longer why haven't we found anyone? The question becomes why would we expect to? This shift in framing is what makes the hypothesis so unsettling to the scientific community. For decades, the default assumption in astrobiology was the principle of mediocrity. This principle says that Earth is not special. The Sun is a typical star. Our solar system is a typical arrangement. Life arose here, so it must arise elsewhere. We are mediocre. We are average. The cosmos is uniform. And what happens here happens everywhere. It is a beautiful democratic idea, and it carries the emotional comfort of belonging. You are not alone because you cannot be alone. The numbers guarantee it. But the rare Earth hypothesis looks at that same data and reaches the opposite conclusion. It says that Earth is not mediocre, it is extraordinary. It says that the Sun is not a typical star, but a star with a very specific set of properties that happen to be ideal for long-term planetary habitability. It says that our solar system is not a typical arrangement, but a freakishly well-organized configuration where the right planets are in the right places doing the right things. It says that the history of life on Earth is not a universal template, but a singular, unrepeatable sequence of accidents, each one of which could have gone differently, and almost certainly did go differently on every other world that tried. This is not arrogance. This is not human exceptionalism dressed up in scientific language. It is the opposite. It is a humbling recognition that the conditions we take for granted, the stability, the complexity, the sheer duration of favorable circumstances, are not the default state of the universe. They are the exception. And exceptions, by definition, are rare. Consider an analogy. Imagine the universe is a vast ocean, trillions of cubic kilometers of salt water stretching in every direction. Now imagine that complex life requires not just water, but a very specific combination of temperature, salinity, mineral content, current patterns, light levels, and chemical gradients, all sustained within a narrow range for billions of years. If you could somehow test every cubic meter of that ocean, you might find that microbial life exists almost everywhere. Hardy little organisms adapted to extremes, thriving in boiling vents and freezing depths. But the conditions for a coral reef, a vibrant, complex, interconnected ecosystem of multicellular organisms, those conditions exist in a tiny, tiny fraction of the total volume. The reef is not impossible. It is just almost incomprehensibly improbable given the size of the ocean. And if two reefs happen to form, they could easily be separated by distances so vast that neither one will ever know the other exists. That is the universe the rare Earth hypothesis describes. An ocean teeming with microbial possibilities but almost devoid of complexity. A cosmos where the ingredients for simple life are scattered generously, but the recipe for a thinking, building, wondering civilization requires a convergence of factors so unlikely that it might happen only once in an entire galaxy, or once in a cluster of galaxies, or once in the entire observable universe. And this brings us to the deepest cut, the one that bothers scientists the most. It is not just the spatial isolation, it is the temporal isolation. Even if complex life does arise somewhere else, even if against all odds another civilization beats the same staggering odds we beat, there is no guarantee it exists at the same time we do. The universe is 13.8 billion years old. Human civilization, the part of it that could even in principle send or receive a signal, is roughly 100 years old. That is a window so narrow it is almost invisible on the cosmic timeline. The distances alone might be insurmountable. But the distances are only half the problem. The other half is time. And time, as we will see, may be the crueler barrier. This is what keeps certain cosmologists awake at night. Not the fear of alien invasion, not the anxiety of cosmic indifference, but the slow, creeping realization that the universe might be structured in such a way that intelligence, by its very nature, is isolated, that the conditions required to produce it are so demanding, and the windows in which it exists are so brief, that even in a universe of unimaginable size and age, two civilizations may never overlap in space or time. Not because of malice, not because of physics preventing it, simply because the math does not work. The numbers do not line up. The probabilities are too thin. And so, we arrive at the question that will carry us through the rest of this story. If the rare Earth hypothesis is correct, or even approximately correct, what does that mean for us? What does it mean to live on a world that might be one of the only places in the entire cosmos where something looked up at the sky and wondered what was out there? What does it mean to be the product of a chain of events so improbable that repeating it would be like shuffling a deck of cards and dealing the same hand twice in a row, not once, but 1,000 times consecutively? It means something profound about the fragility of what we have. It means something uncomfortable about the responsibility we carry. And it means that the silence of the universe, that vast, cold, unanswering silence that has haunted astronomers since the moment they first pointed a radio dish at the stars, might not be a puzzle waiting to be solved. It might be the sound of a cosmos that built something extraordinary exactly once and is still waiting to see what we do with it. The rare Earth hypothesis does not offer comfort. It does not wrap the universe in a warm blanket and tell you everything will be fine. It does the opposite. It strips away the assumption that we are part of a grand cosmic community. It removes the safety net of inevitability. It looks at the evidence, the geological record, the evolutionary timeline, the astrophysical data, and it says that the most honest interpretation of what we know is that complex, intelligent, technological life is not a natural product of the universe. It is a freak accident, a magnificent, terrifying, statistically absurd freak accident, and we are it. The question now is, what conditions are we talking about? Specifically, what is this chain of improbabilities that the hypothesis claims must all be true at once? Because the power of the rare earth argument does not come from vague hand-waving about how special Earth is. It comes from the granular, step-by-step catalogue of specific physical, geological, chemical, and biological requirements that must all be satisfied simultaneously and sustained for billions of years. Each one of these requirements, taken alone, might seem reasonable. Some of them might even seem common, but taken together, multiplied across the full chain, they paint a picture of a universe where the dice must land on the same impossible number over and over again, without a single miss, for billions of years in a row. And that is where the real vertigo begins, because once you see the full list, once you understand just how many things had to go exactly right, you will never look at the night sky the same way again. The stars will still be beautiful, but the spaces between them will feel much, much emptier. Let us play a game. We are going to build a planet. Not just any planet. We are going to build one capable of supporting complex multicellular life for billions of years. Life that can eventually develop eyes, bones, nervous systems, intelligence, and technology. We are going to try to build another Earth, and what you will discover, step by step, is that the universe is not a factory that mass produces habitable worlds. It is a casino. And the game we are playing has so many conditions, so many requirements that must all be met simultaneously that the house always wins. Almost always. To understand why the rare earth hypothesis carries so much scientific weight, you have to see the full chain, not a summary, not a highlight reel, the full, link-by-link catalogue of conditions that Ward, Brownlee, and a growing body of planetary scientists argue must all converge on a single world at a single time and then hold steady for an almost incomprehensible duration. Each link, viewed in isolation, seems manageable. Some even seem likely. But the chain is long, and in probability, length is lethal. It starts with the star. Not all stars are created equal, and the differences matter far more than most people realize. Our Sun is a G-type main sequence star. It is sometimes called a yellow dwarf, though that name undersells its importance. The Sun has a set of properties that, taken together, make it remarkably well suited to hosting a planet with complex life. First, it is stable. It does not flicker violently. It does not erupt with civilization-ending flares every few centuries. It has been burning at a relatively consistent luminosity for roughly 4.5 billion years, and it will continue to do so for several billion more. That steadiness is not a given, it is a gift. Most stars in the galaxy are not like the Sun. Roughly 75% of all stars in the Milky Way are red dwarfs, M-type stars that are smaller, cooler, and dimmer. For a long time, red dwarfs seemed like promising candidates for hosting life. They are abundant, they burn for trillions of years, giving life enormous windows of time to evolve. But there are problems. Serious problems. Because red dwarfs are so dim, the habitable zone around them, the narrow ring where liquid water can exist on a planet's surface, is extremely close to the star. A planet in that zone is so near its parent star that it almost certainly becomes tidally locked, meaning one face permanently points toward the star while the other faces the cold void of space. One hemisphere bakes in eternal daylight, the other freezes in permanent night. The boundary between them is a thin strip of perpetual twilight, battered by ferocious winds as hot air rushes toward the cold side. Maintaining a stable atmosphere under those conditions is extraordinarily difficult, but the bigger threat is the star's temper. Red dwarfs, particularly young ones, are prone to violent stellar flares. These are not minor burps of radiation. They are catastrophic eruptions that can be hundreds or even thousands of times more powerful than anything our Sun produces. A planet huddled close to a red dwarf would be bombarded with X-rays and ultraviolet radiation so intense that it could strip away the atmosphere entirely, sterilize the surface, and destroy any complex molecules trying to form the scaffolding of life. You could have a planet in the habitable zone with liquid water, and it would still be a dead world, its atmosphere peeled away like paint in a sandstorm. On the other end of the spectrum, massive stars, O-type and B-type, burn so hot and so bright that they exhaust their fuel in just a few million years before exploding as supernovae. Complex life on Earth took roughly 4 billion years to emerge. A planet orbiting a massive star would be vaporized long before the first multicellular organism could even think about forming. So the first filter is already in place. You need a star that is bright enough to sustain a habitable zone at a comfortable distance, stable enough to avoid bombarding its planets with lethal radiation, and long-lived enough to give evolution the immense timescales it requires. That eliminates the vast majority of stars in the galaxy. Not all of them, but most. Now you have your star. The next requirement is position. Not just the planet's position relative to the star, but the star's position within the galaxy itself. This is a factor that rarely enters public discussion, but it is central to the rare Earth argument. The Milky Way is not a uniform environment. It is a structured system with distinct regions, and most of those regions are hostile to complex life. The galactic center is a dense, radiation-soaked nightmare. Stars are packed so closely together that gravitational interactions would destabilize planetary orbits. Supernovae are frequent. The supermassive black hole at the core, Sagittarius A star, drives jets and outbursts that would sterilize anything nearby. The outer edges of the galaxy have a different problem. Out there, the abundance of heavy elements, what astronomers call metals, drops dramatically. These heavy elements, carbon, oxygen, iron, silicon, are forged in the cores of stars and scattered by supernova explosions. They are the raw materials of rocky planets and the building blocks of biological chemistry. Without enough of them, you cannot form a rocky planet in the first place, let alone stock it with the elements needed for complex biochemistry. This means there is a galactic habitable zone, a ring within the Milky Way where conditions are just right, not too close to the violent center, not too far into the metal-poor outskirts. Our solar system sits in this zone, roughly 26,000 light-years from the galactic center, in a relatively calm suburban neighborhood between the major spiral arms. This placement reduces the frequency of nearby supernova explosions, gamma-ray bursts, and gravitational disruptions. It is not a guarantee of safety, but it shifts the odds. And in the rare Earth calculus, every shift matters, because every shift is another filter that most star systems fail. So we have a suitable star in a suitable galactic neighborhood. Now we need a planet, and not just any planet. We need a rocky world in the habitable zone with liquid water on its surface. This is the criterion that gets the most public attention, the so-called Goldilocks zone, where temperatures are not too hot and not too cold. But the habitable zone is far more precarious than the nickname suggests. It is not a wide, forgiving band. It is a narrow corridor, and the boundaries shift depending on the star's brightness, the planet's atmospheric composition, its albedo, and dozens of other variables. Earth sits comfortably within our sun's habitable zone today, but if our orbit were just 5% closer to the sun, a runaway greenhouse effect could have turned Earth into Venus, a hellish world with surface temperatures hot enough to melt lead under a crushing atmosphere of carbon dioxide. If our orbit were about 15 to 20% farther out, the planet might have frozen permanently, locking all its water into ice and shutting down the chemical processes that sustain life. The margin is thin, and staying within that margin for billions of years requires a remarkably stable orbit, which itself requires the right gravitational environment, the right planetary neighbors, and a healthy dose of luck. But liquid water on the surface is only the beginning. Let us go deeper, literally, because what happens beneath the surface of a planet may matter even more than what happens on top of it. Earth has plate tectonics. It is the only planet in our solar system confirmed to have active, full-scale plate tectonics, and this process may be one of the most critical and underappreciated requirements for complex life. Plate tectonics is the slow, grinding motion of enormous slabs of rock, tectonic plates, that float on the semi-molten mantle beneath the crust. These plates collide, separate, and slide past each other over millions of years, building mountains, opening ocean basins, and recycling material between the surface and the interior. Why does this matter for life? Because plate tectonics is Earth's thermostat. Over geological time, carbon dioxide builds up in the atmosphere from volcanic outgassing. Left unchecked, this would create a runaway greenhouse effect. But plate tectonics drives a process called the carbonate-silicate cycle. Rain dissolves atmospheric carbon dioxide, forming a weak acid. This acid weathers silicate rocks on the surface, washing the carbon into the ocean. On the ocean floor, the carbon is incorporated into sediments that are eventually dragged down into the mantle at subduction zones, where two plates collide. The carbon is then released again through volcanic eruptions, completing the cycle. This feedback loop has kept Earth's surface temperature within a habitable range for billions of years despite enormous changes in solar luminosity. The sun today is roughly 30% brighter than it was when life first appeared. Without the regulating hand of plate tectonics, Earth would have either frozen solid or boiled over long ago. Complex life would never have had the stable climate it needed to evolve. And plate tectonics is not a simple feature to produce. It requires a planet of the right size, with the right internal heat, the right mantle viscosity, the right crustal composition, and possibly the right amount of water lubricating the subduction zones. Mars, which is smaller than Earth, lost its tectonic activity billions of years ago as its interior cooled. Venus, which is roughly Earth's size, appears to have a stagnant lid regime, where the entire surface is a single unmoving shell that occasionally undergoes catastrophic resurfacing events. Neither planet has the steady recycling engine that Earth possesses, and without it, long-term climate stability is essentially impossible. Next in the chain is a feature that operates invisibly, but without which the surface of the Earth would be a radiation-blasted wasteland: the magnetic field. Earth's core is a dynamo. The outer core is made of liquid iron and nickel, churning through convection currents as the planet rotates. This motion generates a powerful magnetic field that extends far out into space, forming a protective bubble called the magnetosphere. The magnetosphere deflects the solar wind, a constant stream of charged particles pouring out of the sun at hundreds of kilometers per second. Without this shield, the solar wind would gradually strip away the atmosphere, molecule by molecule, leaving the planet exposed. This is not a theoretical concern. It is exactly what happened to Mars. Mars once had a magnetic field. Roughly 4 billion years ago, it lost it as its core cooled and solidified. Without the magnetosphere, the solar wind slowly eroded the Martian atmosphere over hundreds of millions of years. Today, the atmosphere of Mars is less than 1% as dense as Earth's. Any surface water is long gone. Any complex chemistry that might have been developing was snuffed out. A planet can sit perfectly in the habitable zone, have liquid water, have the right chemistry, and still lose everything if it cannot protect its atmosphere from the relentless assault of its own star. Generating and sustaining a strong magnetic field for billions of years requires a planet with a molten outer core that remains convectively active across geological time. That depends on the planet's size, composition, internal heat budget, and possibly even the rate at which heat escapes through the mantle. It is another filter, another condition that must be met and sustained. not for a million years, but for billions. Now let us look up. Above the surface, above the atmosphere, look at the moon. That object hanging in the night sky is not just a scenic backdrop. It may be one of the most important factors in Earth's ability to support complex life. The leading theory for the moon's origin is the giant impact hypothesis. Roughly 4.5 billion years ago, a Mars-sized body, sometimes called Theia, collided with the early Earth in a glancing blow of unimaginable violence. The impact blasted a massive amount of debris into orbit, and over time, that debris coalesced into the moon. This was not a gentle process. It was a world-shattering catastrophe, and it was also, possibly, a prerequisite for our existence. The moon's most critical contribution is gravitational stabilization of Earth's axial tilt. Earth's axis is tilted at roughly 23.4 degrees relative to its orbital plane. This tilt gives us our seasons and distributes solar energy across the planet in a pattern that prevents any single region from becoming permanently baked or permanently frozen. Without the moon's gravitational influence, Earth's axial tilt would not stay fixed. It would wobble chaotically over millions of years, swinging between extremes. Computer simulations have shown that without a large moon, Earth's tilt could vary from nearly 0 degrees, which would eliminate seasons and create extreme temperature differences between equator and poles, to over 60 or even 80 degrees, which would tip the planet so far that the poles would face the sun directly, plunging the world into a climate catastrophe that would make the ice ages look mild. Mars, which has no large moon, experiences exactly this kind of chaotic obliquity variation. Its axial tilt has swung wildly over its history, contributing to dramatic shifts in its climate. For complex life that requires hundreds of millions of years of relative climatic stability to evolve, these kinds of swings are lethal. The moon acts as a gyroscope, a gravitational anchor that keeps Earth's tilt within a narrow, life-friendly range. And getting a moon like ours requires a specific type of giant impact at a specific angle, at a specific time in planetary formation. It is not something that happens to most rocky planets. It is, by all accounts, rare. We are not finished. Turn your attention outward to the architecture of the solar system itself. Specifically, look at Jupiter, that enormous gas giant, more than 300 times the mass of Earth, sitting out in the cold beyond the asteroid belt, has played a role in Earth's history that is easy to underestimate. Jupiter is a gravitational bully. Its immense mass warps the trajectories of comets and asteroids that wander into the inner solar system. Some of these objects get flung out of the solar system entirely. Others get absorbed by Jupiter itself. The famous Shoemaker-Levy 9 comet impact in 1994 demonstrated this vividly. The comet was captured and torn apart by Jupiter's gravity, slamming into its atmosphere in a series of explosions, the largest releasing more energy than the entire nuclear arsenal of humanity combined. Had that comet been aimed at Earth instead, it could have triggered a mass extinction event that would have dwarfed the one that killed the dinosaurs. Now, this is not to say that Jupiter prevents all impacts. Earth has been struck many times throughout its history, and some of those impacts caused devastating mass extinctions. The asteroid that ended the reign of the dinosaurs 66 million years ago is the most famous example. But the rare Earth argument is not that impacts must never happen. It is that they must not happen too frequently. Complex life needs long stretches of relative stability to evolve. If extinction-level impacts occurred every few million years instead of every few 100 million years, complex ecosystems would never have time to recover and diversify. They would be perpetually knocked back to square one. Jupiter, along with Saturn, acts as a partial shield, reducing the frequency of catastrophic impacts to a level that is survivable over geological timescales. Remove Jupiter from the equation, and simulations suggest the impact rate on Earth would increase dramatically enough to potentially prevent complex life from ever gaining a foothold. This is the point where the arithmetic becomes frightening, because none of these conditions operate in isolation. Each one is a prerequisite. Each one is a gate that must be passed. And the chain is not a simple sequence where you clear one hurdle and move to the next. It is a simultaneous requirement. You need the right star and the right galactic position and the right planetary mass and the habitable zone orbit and plate tectonics and the magnetic field and the large stabilizing moon and the protective gas giant and the low impact frequency and the stable long-term climate, all operating at the same time on the same world for billions of years without interruption. Think of it as a combination lock, but instead of 4 digits, there are a dozen, maybe more. Each dial has a range of possible values, and only a tiny fraction of those values represent the correct setting. If one dial is off by even a small amount, the lock does not open. No partial credit, no close enough. The lock opens only when every single dial is set precisely within the correct range. Now, imagine spinning those dials randomly across trillions of planets. What are the odds that any given planet lands on the correct combination? If each condition has even a 1 in 10 chance of being met, which is generous for many of them, and there are 12 independent conditions, the combined probability is 1 in a trillion. One planet out of every trillion would have the right combination. The Milky Way contains a few 100 billion planets. That math suggests that in our entire galaxy, the expected number of planets meeting all the criteria might be less than 1. We might be that less than 1. We might be the rounding error that somehow became real. And we have not even discussed the biological filters yet. We have not talked about the specific evolutionary transitions that had to occur after all these physical conditions were met. We have only built the stage. We have not yet asked whether the actors can even learn their lines, because having a planet with the right star, the right orbit, the right geology, the right magnetic field, the right moon, and the right planetary neighbors does not automatically produce a technological civilization. It produces an opportunity, a ticket to the next round of the lottery. And that next round, the biological gauntlet from microbe to mind, has its own chain of improbabilities, its own set of gates that must be passed, its own history of events so rare that they happened only once in 4 billion years on the one planet we know had every advantage. What the rare Earth hypothesis forces you to confront is not just the vastness of space, but the precision of existence. We are not talking about a universe that is empty because it is hostile. We are talking about a universe that is empty because it is specific. The requirements are not arbitrary. They are rooted in physics, chemistry, and biology. They are the actual conditions that real science has identified as necessary for what happened on Earth to happen at all. And when you lay them out, link by link, filter by filter, the picture that emerges is not one of a cosmos eager to produce complexity. It is a picture of a cosmos that is overwhelmingly indifferent to it. A cosmos where the default state of a planet is sterile, frozen, irradiated, or geologically dead. Where the exception, the glorious, improbable exception, is a world like ours. That realization is the foundation on which everything else in this story rests. Because if the physical conditions are this demanding, then the biological journey that follows, the 4 billion year odyssey from the first cell to the first thought, becomes not just unlikely but almost miraculous. And understanding why requires us to look at something most people never consider: the gulf between a microbe and a mind. The distance between life that exists and life that knows it exists, a distance so vast that the universe may have crossed it only once. Let us do something that sounds simple but is actually one of the most humbling exercises in all of science. Let us compress the entire history of life on Earth into a single 24-hour clock. Midnight represents the formation of the planet, roughly 4.5 billion years ago. The present moment is the next midnight, 24 hours later. Each hour on this clock represents approximately 187 million years. Each minute is about 3 million years. Each second is roughly 52,000 years. Now, watch the clock. By around 3:30 in the morning, the first simple microbial life appears. Single-celled organisms, prokaryotes, tiny bags of chemistry with no nucleus, no internal structure, just membranes and molecules doing the bare minimum to qualify as alive. That is fast. Remarkably fast. Less than 4 hours into our 24-hour day, and life has already started. This speed is one of the reasons many scientists believe simple life might be common across the universe. The jump from chemistry to biology seems to happen almost eagerly, as if the universe is biased toward it. But now, watch what happens next. Or rather, watch what does not happen. For the next 17 hours, almost nothing changes. From 3:30 in the morning until roughly 8:30 in the evening, the planet is ruled entirely by single-celled microorganisms. No animals, no plants, no fungi, no eyes, no legs, no brains. Just single-celled microbes, floating, dividing, metabolizing, existing in vast, undifferentiated monotony for nearly 3 billion years. That is not a brief intermission. That is most of the show. If you sat down to watch the movie of life on Earth, you would spend more than 70% of the runtime staring at a world of slime. The first eukaryotic cells, cells with a true nucleus and internal compartments, do not appear until somewhere around 2 in the afternoon. Multicellular life does not emerge until roughly 8:30 in the evening. The Cambrian explosion, that sudden burst of complex animal body plans that fills the fossil record with creatures that finally look like something, does not happen until approximately 9:20 at night. Dinosaurs appear around 10:40. They go extinct at 11:39. The entire history of the genus Homo, every species of human that has ever lived, occupies the last 4 seconds before midnight. And modern technological civilization, the part that can build telescopes and wonder about alien life, takes up less than the final millisecond. Stare at that timeline. Really absorb it, because it tells you something critical about the rare Earth hypothesis that the physical conditions alone cannot convey. Even on a planet that has every advantage, even on a world with the right star, the right orbit, plate tectonics, a magnetic field, a stabilizing moon, and a protective gas giant, the journey from simple life to complex life is not a smooth escalator. It is not an inevitable progression where one thing naturally leads to the next. It is a brutal obstacle course littered with bottlenecks so narrow that life on Earth barely squeezed through them, and in most cases, squeezed through only once. This is the biological core of the rare Earth argument. It is not enough to have a habitable planet. It is not enough to have microbial life. To get from a bacterium to a being that can contemplate its own existence requires a series of specific evolutionary transitions, each of which appears to be extraordinarily improbable, not impossible. Obviously not impossible, because it happened here, but so unlikely that it may represent the true bottleneck, the real filter that separates a universe peppered with microbes from a universe populated by civilizations. Let us walk through these transitions one at a time, because each of them is a story unto itself, and each of them carries a weight that most people never appreciate. The first great bottleneck is the origin of the eukaryotic cell. For roughly the first 2 billion years of life on Earth, every living organism was a prokaryote. Simple, small, lacking a nucleus or any internal membrane-bound structures, prokaryotes are extraordinarily successful. They dominate the planet to this day in sheer numbers and biomass, but they have a ceiling. They can only get so big. They can only get so complex. Their energy production is tied to their cell membrane, and as a cell grows larger, the ratio of membrane surface area to internal volume drops. They cannot generate enough energy per gene to support the vast genomes required for complex multicellular life. They are efficient, resilient, and ancient, but they are stuck. The breakthrough came in the form of an event so unlikely that it appears to have happened exactly once in the entire history of life on Earth. One prokaryotic cell engulfed another, and instead of digesting it, the two formed a permanent partnership. The engulfed cell became the mitochondrion, the powerhouse of the eukaryotic cell. This event is called endosymbiosis, and it was first convincingly proposed by biologist Lynn Margulis in the late 1960s, though the idea was initially met with fierce resistance. The evidence is now overwhelming. Mitochondria have their own DNA. They have double membranes. They replicate semi-independently within the cell. They are the remnants of what were once free-living bacteria that became permanently incorporated into a host cell roughly 2 billion years ago. Why is this such a critical bottleneck? Because it was not just one lucky event. It was a specific type of lucky event that required a precise set of conditions. The host cell had to engulf the smaller cell without destroying it. The smaller cell had to survive inside the host without being digested. The two had to develop a stable metabolic relationship where the smaller cell provided energy and the host provided protection and resources. Gene transfer had to occur between the two genomes, with many of the smaller cell's genes migrating into the host nucleus over millions of years. The resulting hybrid had to be more successful than either partner alone, and this entire process had to avoid being disrupted by any of the countless things that can go wrong when two organisms try to merge into one. The evolutionary biologist Nick Lane has argued extensively that this single event, the acquisition of mitochondria, was the key that unlocked all subsequent complexity. Without the energy surplus provided by mitochondria, eukaryotic cells could never have supported the enormous genomes needed for multicellular life. They could never have built the intricate cellular machinery required for differentiated tissues, organs, and body plans. Every complex organism on Earth, every animal, every plant, every fungus is a eukaryote. And every eukaryote traces its ancestry back to that single, unrepeated merger. 2 billion years of prokaryotic life preceded it. In all that time, across all those trillions upon trillions of microbial generations, it happened once, not twice. Not independently on different continents or in different oceans, once. That singularity is a powerful piece of evidence. It suggests that the event was not an inevitable consequence of microbial evolution. It was a fluke. A cosmic accident that happened to work out on one planet, orbiting one star in one arm of one galaxy. And without it, the entire trajectory of complex life never begins. But endosymbiosis alone is not enough. The second great bottleneck is the transition to true multicellularity. Having a eukaryotic cell is like having a more powerful engine. It gives you potential. But potential is not the same as achievement. For hundreds of millions of years after the first eukaryotes appeared, they remained single-celled. They floated through ancient oceans as individual organisms, eating, dividing, dying. The transition to multicellularity, where individual cells begin cooperating as a unified organism with specialized tissues and division of labor, is a leap of staggering complexity. It requires cells to give up their individual reproductive freedom for the benefit of the collective. It requires the evolution of genetic programs that control cell differentiation, telling one cell to become muscle and another to become nerve and another to become skin. It requires mechanisms to prevent cheating, to stop rogue cells from reverting to selfish behavior and hijacking the organism. This is essentially the problem of cancer. Cancer is what happens when multicellular cooperation breaks down, when a cell abandons its role in the collective and starts proliferating for its own benefit. The fact that cancer is so common, that it afflicts virtually every multicellular lineage on Earth, tells you how fragile and difficult multicellular cooperation actually is. evolution had to develop elaborate tumor suppression systems, cell death programs, and immune surveillance just to keep the whole project from collapsing. Now, it is true that multicellularity has evolved independently multiple times on Earth. Estimates range from roughly 25 to over 40 separate origins, depending on how broadly you define it. Plants, animals, fungi, and several lineages of algae all evolved multicellularity independently. This might suggest that it is not a particularly difficult transition, but there is a critical caveat. Most of these independent origins produced only simple multicellularity, clumps of cells, films, filaments, sheets, the kind of multicellularity that produces complex body plans with differentiated tissues and organs, the kind that produces an animal with a nervous system. That kind of multicellularity appears to have evolved only a handful of times, and the most sophisticated version, the one that produced the animal kingdom, appears to have evolved only once. Simple multicellularity may be relatively easy. Complex multicellularity is not. The third bottleneck is sexual reproduction. This might seem like a strange entry on the list. After all, sex is everywhere in the biological world. But the evolution of sex is one of the deepest puzzles in biology. Asexual reproduction is simpler, faster, and more efficient. An organism that reproduces asexually passes on 100% of its genes to every offspring. An organism that reproduces sexually passes on only 50%. From a purely genetic accounting standpoint, sex is a terrible deal. It is expensive. It requires finding a mate. It introduces the risk of sexually transmitted diseases. It wastes time and energy. And yet, the vast majority of complex eukaryotic lineages reproduce sexually. Why? The leading explanations center on genetic diversity. Sexual reproduction shuffles genes between individuals, creating new combinations in every generation. This variation is the raw material of natural selection. It allows populations to adapt faster to changing environments. It helps purge harmful mutations that would otherwise accumulate in asexual lineages. It provides a defense against parasites, which must constantly evolve to keep up with a moving target of genetic diversity. Without sexual reproduction, the pace of evolutionary innovation slows to a crawl. Complex organisms become sitting ducks for parasites and environmental change. The emergence of sex appears to have been a prerequisite for the kind of rapid diversification that eventually produced complex animals. And while the exact timing and mechanism of its origin remain debated, it was clearly a pivotal transition that transformed the trajectory of life on this planet. The fourth bottleneck is arguably the most dramatic event in the history of life on Earth. It is the Cambrian explosion. For the first 3 billion years, life was overwhelmingly microscopic. Even after eukaryotes evolved and multicellularity appeared, the organisms were small and simple. Then, roughly 540 million years ago, something extraordinary happened. In a geological eye blink of perhaps 20 to 25 million years, almost every major animal body plan that exists today appeared in the fossil record. Eyes, legs, shells, claws, spinal cords, segmented bodies, jaws, gills. The sudden profusion of complex animal forms was so abrupt and so dramatic that Darwin himself considered it one of the most serious objections to his theory of evolution by natural selection. He expected the fossil record to show gradual transitions. Instead, it showed an explosion. What triggered it? The causes are still debated, but several factors likely converged. Rising oxygen levels in the atmosphere and oceans, driven by billions of years of photosynthetic cyanobacteria, finally crossed a threshold that could support the metabolic demands of large, active animals. An evolutionary arms race between predators and prey may have driven rapid diversification. As organisms competed for survival, by developing ever more sophisticated body plans. The evolution of key genetic toolkits, particularly the Hox genes that control body plan development, may have reached a level of complexity that suddenly made new forms possible. Whatever the combination of causes, the Cambrian explosion was a singular event. Nothing like it has happened before or since. It was the moment when life shifted from simple to spectacularly complex, and it required a convergence of atmospheric, oceanic, genetic, and ecological conditions that had been building for billions of years. Remove any one of those preconditions, and the explosion might never have ignited. The fifth bottleneck is the colonization of land. For the first 4 billion years, life was confined to the oceans. The land surface of the planet was a barren, hostile desert. No soil, no shade. Punishing ultraviolet radiation from the sun, mitigated only when the ozone layer built up sufficiently from atmospheric oxygen. The transition from water to land required organisms to solve a cascade of engineering problems simultaneously. They needed structural support to resist gravity, which water had been providing for free. They needed new methods of gas exchange. Since gills do not work in air, they needed protection against desiccation. They needed new reproductive strategies, since releasing eggs and sperm into water was no longer an option. Plants solved these problems first, colonizing land roughly 470 million years ago, and gradually creating the soil and shade that made terrestrial life possible for animals. Arthropods followed, then amphibians, then reptiles, then mammals. Each step required its own suite of adaptations, its own improbable innovations, and the entire process depended on the prior establishment of an ozone layer, which depended on atmospheric oxygen levels, which depended on billions of years of photosynthesis by single-celled organisms in the oceans. The chain of dependencies stretches back to the very beginning. The sixth bottleneck is the evolution of intelligence. And this is where the rare earth argument becomes most sobering. We tend to think of intelligence as an inevitable product of evolution. We assume that given enough time, brains will naturally get bigger and smarter, that evolution trends toward greater complexity and greater cognitive ability. But this assumption is not supported by the evidence. Evolution does not have a direction. It does not aim for intelligence. It selects for survival and reproduction in whatever environment an organism happens to occupy. For most of Earth's history, intelligence was not only unnecessary, it was metabolically expensive. The human brain accounts for roughly 2% of body mass, but consumes approximately 20% of the body's energy at rest. That is an enormous cost. An organism that invests that much energy in a brain had better get a spectacular return on that investment, or natural selection will punish it. Most lineages on Earth have thrived for hundreds of millions of years without anything resembling intelligence. Bacteria have been successful for nearly 4 billion years with no brain at all. Insects have dominated terrestrial ecosystems for over 400 million years with brains smaller than a grain of rice. Sharks have patrolled the oceans for 450 million years with cognitive abilities that are, by any human standard, extremely limited. Intelligence of the kind that leads to technology, language, abstract thought, and civilization appears to have evolved exactly once, not in the dinosaurs, who had over 160 million years to develop it and never did, not in the cephalopods, despite their remarkable cognitive abilities, not in the corvids or the cetaceans, despite their impressive social intelligence. Only in one lineage, the great apes, and only in one species within that lineage, did the specific combination of large brain, bipedalism, free hands, social cooperation, language, and tool use converge to produce a technological civilization. And that convergence depended on a chain of contingent events that stretches back through millions of years of primate evolution, through the extinction of the dinosaurs that opened ecological niches for mammals, through the specific climate changes that transformed African forests into savannas and forced our ancestors to adapt to a new way of life. Change any one of those contingencies, and we do not arrive at this moment. This is the pattern that the rare earth hypothesis highlights. Not one bottleneck, not one improbable event. A cascading series of them, stacked on top of each other like a tower of cards. Endosymbiosis, complex multicellularity, sexual reproduction, the Cambrian explosion, the colonization of land, the evolution of intelligence, each one dependent on the ones before it, each one staggeringly unlikely in isolation, and the probability of all of them occurring in sequence, on the same planet, under the right conditions, within the available time window, is a number that makes the physical requirements we discussed earlier look generous by comparison. And here is the final, quietest piece of the argument. Time. Complex life on Earth did not appear overnight. It required roughly 4 billion years of uninterrupted planetary habitability. 4 billion years during which the sun did not flare catastrophically, during which no rogue star passed close enough to destabilize the orbits of the planets, during which no gamma ray burst from a nearby supernova sterilized the surface, during which plate tectonics continued to regulate the climate, during which the magnetic field continued to shield the atmosphere, during which no asteroid large enough to end the experiment struck at the wrong moment. 4 billion years is not just a long time, it is a long time during which nothing can go catastrophically wrong. And the universe is very good at making things go catastrophically wrong. Most planets will not enjoy 4 billion years of stability. Most will be disrupted long before complex life has a chance to emerge. Their stars will vary, their orbits will shift, their magnetic fields will fail. Their atmospheres will be stripped, their surfaces will be sterilized, the clock will reset, and the painstaking, achingly slow process of biological evolution will have to start over from scratch, if it can start at all. This is why a galaxy full of microbes but empty of civilizations is not a paradox under the rare earth hypothesis. It is the natural result. Simple life may spring up wherever liquid water and chemistry allow. It may be as common as mud, but complex life, the kind that eventually produces technology and wonder and the ability to look up and ask whether anyone else is out there. That kind of life requires a convergence of physical, geological, chemical, and biological conditions so specific and so prolonged that it may be the rarest phenomenon in the cosmos. Not because the universe forbids it, but because the universe is indifferent to it, and indifference, multiplied across trillions of planets and billions of years, produces emptiness. So, we have built the stage, and we have catalogued the biological odyssey that must unfold upon it. We have seen that the requirements are staggering, both in their specificity and in their duration. And now we must turn to the question that all of this inevitably raises, the question that has haunted astronomers and philosophers for decades, the question that the rare earth hypothesis answers, not with drama, but with a quiet, unsettling clarity. If all of this is true, if the conditions for complex life are this demanding and the biological journey is this improbable, then what should we expect when we look out into the galaxy? What should we hear when we point our radio telescopes at the stars? And what does it mean that the answer, so far, has been nothing at all? In the summer of 1950, the physicist Enrico Fermi was having lunch with colleagues at Los Alamos National Laboratory. The conversation had drifted, as conversations between physicists often do, toward the topic of extraterrestrial life. Flying saucer reports were in the news at the time, and the scientists were joking about them. But then Fermi, who had a legendary ability to cut through noise and find the core of a problem, asked a question that stopped the table cold. He said, simply, "Where is everybody?" The question was not rhetorical, it was mathematical. Fermi had done the calculation in his head the way most people add up a restaurant bill. The galaxy is roughly 13 billion years old. It contains hundreds of billions of stars. Even if the probability of intelligent life arising around any given star is tiny, the sheer number of stars should produce at least some civilizations. And if even one of those civilizations developed the desire and the ability to spread across the galaxy, using self-replicating probes or colony ships traveling at even a modest fraction of the speed of light, the entire Milky Way could be colonized in a few tens of millions of years. That sounds like a long time, but it is less than 1% of the galaxy's age. There has been more than enough time for this to happen, not once, many times over. So where are the megastructures? Where are the Dyson spheres? Where are the radio signals, the probes, the artifacts? Where is the evidence that anyone else has ever existed? The table went quiet because no one had a good answer. That question, now known as the Fermi Paradox, has been gnawing at the scientific community for over 70 years. It has spawned an entire cottage industry of proposed solutions, from the optimistic to the terrifying. Perhaps civilizations destroy themselves before they can spread. Perhaps they are hiding. Perhaps they have transcended physical existence. Perhaps they are already here and we cannot recognize them. Each proposed answer carries its own emotional flavor, its own implications for what kind of universe we live in. But the rare Earth hypothesis offers something that many of the more dramatic solutions do not. It offers a simple answer. An answer grounded not in speculation about alien psychology or hypothetical super technologies, but in the hard data of planetary science, evolutionary biology, and astrophysics. The rare Earth answer to the Fermi paradox is this: we do not see anyone because there is almost certainly no one to see. Not because civilizations are hiding, not because they have destroyed themselves, not because the universe is teeming with intelligence that we cannot detect, but because the conditions required to produce complex, technological life are so extraordinarily specific, and the biological journey from microbe to mind is so extraordinarily improbable, that the expected number of civilizations in our galaxy may be exactly one, us. And the silence of the cosmos is not a mystery. It is the sound of a prediction confirmed. Let us trace this reasoning carefully, because its power lies in its precision. We have already catalogued the chain of conditions that the rare Earth hypothesis identifies as necessary for complex life. A stable, long-lived G-type star, a position within the galactic habitable zone, a rocky planet in the circumstellar habitable zone, plate tectonics, a strong magnetic field, a large stabilizing moon, protective gas giants, a low frequency of catastrophic impacts, billions of years of climate stability, and then, on top of all of that, the biological gauntlet, the origin of eukaryotic cells through endosymbiosis, the evolution of complex multicellularity, sexual reproduction, the Cambrian explosion, the colonization of land, the evolution of intelligence, the development of technology. Each of these is a probability filter. Each one reduces the number of planets that make it through to the next stage. And when you multiply the filters together, the number does not just shrink, it collapses. Consider a deliberately generous version of this calculation. Suppose there are 200 billion stars in the Milky Way. Suppose half of them have planetary systems. That gives us 100 billion systems. Now, suppose 1 in 5 of those systems has a rocky planet in the habitable zone, 20 billion candidate worlds, generous so far. Now start applying the filters. Suppose 1 in 10 of those planets orbits a star with the right stability and longevity. 2 billion. Suppose 1 in 10 of those has plate tectonics. 200 million. Suppose 1 in 10 has a strong enough magnetic field sustained over billions of years. 20 million. Suppose 1 in 10 has a large stabilizing moon formed by the right kind of giant impact. 2 million. Suppose 1 in 10 sits in a solar system architecture with the right protective gas giants. 200,000. Suppose 1 in 10 maintains climate stability long enough for complex life to evolve. 20,000. We are already down to 20,000 planets in the entire galaxy that meet just the physical prerequisites. And we have been generous at every single step. We have not even touched the biological filters yet. Now apply them. Suppose 1 in 100 of those planets manages the transition from prokaryotic to eukaryotic life through endosymbiosis. 200. Suppose 1 in 10 of those achieves complex multicellularity. 20. Suppose 1 in 10 develops sexual reproduction and the kind of genetic innovation that drives rapid diversification. 2. Suppose 1 in 10 undergoes something comparable to the Cambrian explosion. The number is now less than 1. We have run out of planets. And remember, at every step we used optimistic estimates. If any of those filters are harder than 1 in 10, if the probability of endosymbiosis is 1 in 1,000 instead of 1 in 100, if the probability of intelligence evolving is 1 in 1,000,000, then the expected number drops so far below 1 that the entire observable universe might not contain a second example. This is not a proof. It is an exercise in probability, and the inputs are uncertain. We do not know the true probability of plate tectonics on a random rocky planet. We do not know how unlikely endosymbiosis really is. We are estimating, extrapolating, making educated guesses based on a sample size of 1. But the structure of the argument is sound. And the structure says that even with generous assumptions, the number of technological civilizations in the galaxy is almost certainly very small. Possibly 1, possibly 0 if we are being strict about it and we happen to be the statistical outlier that got through. But let us be even more generous. Let us assume the rare Earth hypothesis is partially wrong. Let us assume that some of the conditions it identifies are not as strict as claimed. Perhaps plate tectonics is more common than we think. Perhaps a large moon is not as critical as the models suggest. Perhaps intelligence evolves more readily than one single example implies. Let us grant all of that. Let us say that instead of 1 civilization per galaxy, there are 10, or 100, or even 1,000 scattered across the Milky Way's vast spiral arms. Does that solve the problem? Does that explain the silence? It does not, because even 1,000 civilizations in a galaxy of 200 billion stars would be separated by staggering distances. The Milky Way is roughly 100,000 light-years across. If 1,000 civilizations were distributed evenly throughout the galactic disk, the average distance between any two of them would be several thousand light-years. A radio signal broadcast from one of them would take thousands of years to reach the nearest neighbor. A reply would take thousands more. A round-trip conversation would span longer than the entirety of recorded human history. And that assumes both civilizations are broadcasting at the same time, in the same direction, at the same frequency, with enough power to be detected across that distance. The odds of those conditions aligning are, to put it gently, not encouraging. This brings us to a factor that is often overlooked in popular discussions of the Fermi Paradox, but that the rare Earth hypothesis makes painfully clear. The problem of time. We tend to imagine civilizations as permanent fixtures, like cities on a map that once built stay there forever. But civilizations are not permanent. They are processes. They rise and they fall. They emerge, they flourish, and they either collapse or transform into something unrecognizable. The average duration of a civilization capable of interstellar communication is one of the great unknowns in this field, and the estimates range wildly. Optimists suggest millions of years. Pessimists suggest a few hundred. The only data point we have is ourselves, and our track record is not reassuring. Human civilization has existed in its current technological form for roughly a century. We have had the ability to broadcast radio waves into space for about 120 years. We have had nuclear weapons for 80. We have been aware of climate change as an existential threat for roughly 40. Whether we will still exist as a technological species in 500 years, let alone 5,000 or 5 million, is a question nobody can answer with confidence. Now, project this uncertainty onto the galactic stage. The Milky Way is 13 billion years old. Imagine a civilization that arose 5 billion years ago, flourished for 10,000 years, and then collapsed. Their radio signals washed across the galaxy and faded into the background noise of the cosmos long before our solar system even formed. They are gone. Their ruins, if any survived, are buried under billions of years of geological change on a planet we will never visit. They might as well have never existed as far as we are concerned. Now imagine another civilization that will arise 3 billion years from now, long after our sun has swollen into a red giant and swallowed the Earth. They will look out at the galaxy and see the same silence we see. They will ask the same question Fermi asked, and the answer will be the same. Not because the galaxy is empty of life across all of time, but because the windows do not overlap. This is the temporal isolation problem, and it is devastating. Even if the rare Earth hypothesis is too pessimistic, even if civilizations arise more often than the strictest version of the argument predicts, they may still be so widely spaced in time that they never coexist. Picture a dark room. Imagine that once every million years, a single firefly blinks somewhere in that room. The blink lasts for 1 second. Over the course of 1 billion years, 1,000 fireflies will have blinked. The room is not empty of light, but if you walk into that room at any random moment, the odds of seeing a blink are essentially 0. You would stand in the darkness, straining your eyes, and conclude that you are alone. You would be wrong in the absolute sense. Fireflies have blinked and will blink again. But you would be right in every practical sense. The darkness is your reality. The blinks are separated by gulfs of time so vast that they might as well be in different universes. This is the condition the rare Earth hypothesis describes for our galaxy. Not necessarily a galaxy devoid of life across all of space and time, but a galaxy where the conditions for complex life are so rare and the windows of technological civilization so brief that the chance of two civilizations existing close enough in space and time to detect each other rounds to 0. The silence is not strange. The silence is the expected outcome. The Fermi Paradox is not a paradox at all under this framework. It is a straightforward consequence of the math. And this reframing changes the emotional texture of the silence in a way that is worth pausing to appreciate. Most proposed solutions to the Fermi Paradox carry a charge of menace. The Great Filter implies that something is out there killing civilizations. The dark forest theory implies that something is out there hunting them. Self-destruction hypotheses imply that intelligence is inherently suicidal. These are dramatic, frightening narratives. They turn the silence into a warning. But the rare Earth answer carries a different kind of weight. It is not dramatic. It is not frightening in the way that a predator is frightening. It is sad, not because the universe forbids it, but because the universe does not care whether it happens or not. And a cosmos that does not care, multiplied across trillions of planets and billions of years, produces emptiness. The silence is not a threat. It is a fact about how rare we are. Some scientists find this framing more disturbing than the alternatives. A universe with hostile aliens is at least a universe with company. It is a universe where intelligence arises regularly, even if it behaves badly. There is something almost comforting about the idea that the galaxy is full of life, even dangerous life. It confirms that what happened on Earth is natural, expected, repeatable. But a universe where we are essentially alone, where intelligence is a statistical anomaly so extreme that it might happen once per galaxy or less, that universe offers no such comfort. It says that what happened on Earth was not natural in the sense of being common. It was natural in the sense of being possible, but so wildly improbable that it approaches the miraculous without ever crossing into the supernatural. There is another dimension to this isolation that deserves attention, because it addresses a hope that many people cling to when confronted with the rare Earth hypothesis. The hope goes like this: even if complex life is rare in our galaxy, the observable universe contains roughly 2 trillion galaxies. Surely across that enormous volume, other civilizations must exist somewhere, and that is probably true. Even if the odds are 1 in a galaxy or 1 in 10 galaxies, the sheer number of galaxies in the observable universe makes it likely that other technological civilizations exist or have existed at some point in cosmic history. But this hope contains a hidden cruelty, because the observable universe is 93 billion light-years across, and it is expanding. The nearest large galaxy to our own, Andromeda, is 2.5 million light-years away. A radio signal sent from a civilization in Andromeda would take 2.5 million years to reach us. And by the time it arrived, the civilization that sent it might have been dead for 2 million years. The distances between galaxies are so vast, and the expansion of space is so relentless, that civilizations in different galaxies are, for all practical purposes, in different universes. They cannot communicate, they cannot interact, they cannot even confirm each other's existence within any reasonable time frame. So yes, other civilizations may exist somewhere in the observable universe, but they are separated from us by distances so enormous that the word isolation does not begin to capture the reality. We are not just alone in our galaxy, we are alone in our accessible universe. The rest is beyond our reach, receding into the dark at an accelerating pace, carrying whatever wonders it contains into a silence that will never be broken. This is the picture that the rare Earth hypothesis paints when you follow its logic to the end. Not a galaxy teeming with life that we have not yet found. Not a cosmos full of hidden civilizations waiting for the right moment to reveal themselves. But a universe where the overwhelming default state is emptiness. Where the conditions for complex life are so rare that they might converge only a handful of times across the entire observable cosmos. Where those handful of civilizations, if they exist at all, are separated by distances measured in millions of light-years and timescales measured in billions of years. Where the silence is not a puzzle to be solved but a truth to be absorbed. And it is worth noting that this picture is becoming harder to dismiss as our observational capabilities improve. For decades, the optimists could argue that we simply had not looked hard enough. Our telescopes were too weak. Our surveys were too narrow. Give us more data, and the galaxy will reveal its inhabitants. But the data is coming in, and so far, it supports the rare Earth position more than it undermines it. The Kepler Space Telescope, launched in 2009, surveyed over 150,000 stars and discovered thousands of exoplanets. It confirmed that planets are common. Rocky planets in habitable zones exist by the billions, but having a rocky planet in a habitable zone is only the first and easiest step in the rare Earth chain. None of those discoveries tell us anything about plate tectonics, magnetic fields, stabilizing moons, or the biological bottlenecks that lie beyond. The James Webb Space Telescope is beginning to analyze the atmospheres of exoplanets, looking for biosignatures, chemical fingerprints that might indicate the presence of life. If it detects oxygen and methane in the atmosphere of a rocky world in the habitable zone, that would be a monumental discovery. It would suggest that simple life is indeed common, but it would also, paradoxically, strengthen the rare Earth argument in one critical way. It would confirm that the bottleneck is not the origin of simple life. The bottleneck is the vast, treacherous journey from simple life to complex life. Finding a galaxy full of microbial biosignatures, but devoid of technosignatures, would be exactly the outcome the rare Earth hypothesis predicts. Microbes everywhere, minds nowhere. SETI has been searching for radio signals and other technosignatures for over 60 years. The search has grown more sophisticated with each decade. Breakthrough Listen, funded by Yuri Milner, is the most ambitious SETI program ever conducted, surveying over 1 million stars across multiple frequency bands with unprecedented sensitivity. So far, the result has been unbroken silence. No confirmed signals. No anomalous patterns. No whispers from the dark. This does not prove that no one is out there. Absence of evidence is not evidence of absence, as the saying goes. But as the search expands and the silence persists, the weight of that silence grows heavier. It becomes increasingly difficult to argue that the galaxy is full of chatty civilizations, and we have simply been unlucky in our search. At some point, the absence of evidence does become evidence of absence, or at least evidence that whatever is out there is far rarer and far quieter than the optimists hoped. So, we arrive at a place of stark clarity. The rare Earth hypothesis does not solve the Fermi Paradox with a dramatic revelation. It does not announce that aliens are real but dangerous, or that we are living in a simulation, or that a cosmic predator is responsible for the silence. It solves the paradox by dissolving it. It says that the paradox only exists if you begin with the assumption that complex life should be common. Remove that assumption, replace it with a careful, evidence-based assessment of what complex life actually requires, and the paradox vanishes. The silence becomes expected. The emptiness becomes natural. The loneliness becomes the default state of a universe that produces stars and planets with breathtaking generosity, but produces minds with agonizing rarity. And that realization, quiet as it is, carries an enormous weight, because if we are alone, or functionally alone, or alone in every way that matters within the reach of our instruments and our lifetimes, then everything we do carries a significance that most people have never contemplated. Every war we fight, every forest we burn, every species we drive to extinction, every political squabble we elevate to existential importance is happening on a stage that may be unique, not just rare, not just special, possibly singular. If this is the only place in the galaxy where something looks up and wonders, then the stakes of our choices are not measured in human terms, they are measured in cosmic terms. And the question of what we owe to the future, to our planet, to the fragile web of conditions that produced us, becomes the most important question our species has ever faced. That is the weight of being rare. And it is to that weight and what it demands of us that we must now turn. There is a moment that astronauts describe almost universally when they first see Earth from orbit. They call it the overview effect. It is not simply the beauty of the planet that strikes them, though the beauty is overwhelming. It is something deeper, something that rewires how they think about existence. They look down and see a thin, luminous shell of atmosphere clinging to a ball of rock suspended in absolute blackness. No borders visible, no nations, no ideologies, just a single, fragile, glowing sphere floating in an ocean of nothing. And what hits them, what physically changes the expression on their faces, is the realization that everything they have ever known, every person who has ever lived, every song ever sung, every war ever fought, every act of love and cruelty and wonder in the entire history of the human species happened on that tiny dot. Nowhere else. There is nowhere else. The blackness around it is not just empty, it is incomprehensibly vast and, as far as any instrument has ever been able to determine, incomprehensibly silent. The overview effect is not an intellectual conclusion. It is an emotional earthquake. It is the moment when the abstraction of cosmic loneliness becomes visceral. Now imagine that feeling amplified by everything we have discussed. Imagine looking at that thin blue arc of atmosphere and understanding, truly understanding, that the chain of events which produced it may never have been repeated anywhere within reach, that the plate tectonics churning beneath its surface are not a common feature of rocky worlds but a geological anomaly, that the magnetic field shielding its atmosphere is powered by a molten iron dynamo that most planets lose within their first billion years, that the oversized moon stabilizing its axial tilt was born from a collision so specific it might as well have been choreographed, that the gas giant standing guard in the outer solar system has been deflecting extinction-level impacts for billions of years, buying time for evolution to do its slow, painstaking, unimaginably improbable work. Imagine knowing all of that, and then looking at the blackness beyond the atmosphere, and understanding that it is not waiting to be filled, it is simply empty. The rare Earth hypothesis does not just change how we think about the universe, it changes how we think about ourselves. And the shift is not toward grandiosity, it is toward gravity. Not the kind that bends space-time, the kind that bends the conscience. Let us sit with the loneliness for a moment, because it deserves more than a passing acknowledgement. Human culture has been shaped by the assumption that we are not alone. Our mythologies are filled with gods who descend from the heavens. Our religions place us in a created order alongside other intelligences, angels, spirits, beings of light. Our science fiction imagines a galaxy buzzing with civilizations, some friendly, some hostile, but always present, always out there. The idea that the cosmos is populated runs so deep in our collective psychology that we rarely examine it. It is a background assumption, like the solidity of the ground or the direction of gravity. The rare Earth hypothesis pulls that assumption out from under us, and what it leaves behind is not a void of meaning. It is a recalibration of meaning so profound that most people instinctively resist it. Consider what it would mean, emotionally and philosophically, if the scientific community reached a consensus that complex life is vanishingly rare, not extinct elsewhere, not hiding, not waiting to be discovered, simply absent. Imagine that the James Webb Space Telescope surveys thousands of exoplanet atmospheres and finds biosignatures of microbial life on dozens of worlds, confirming that simple life is indeed common. But imagine that simultaneously, SETI completes a comprehensive survey of the nearest million stars and finds nothing. No signals, no technosignatures, no Dyson spheres, no megastructures. Imagine that, century after century, as our instruments grow more powerful and our surveys grow more complete, the answer remains the same. Microbes, yes. Minds, no. The optimists would keep hoping. They would say, the search is not finished. And they would be right in a technical sense, because you can never prove a universal negative. But at some point, the weight of evidence would shift the conversation. The question would no longer be, are we alone? The question would become, what do we do now that we know? That question is where the rare Earth hypothesis stops being an abstract scientific argument and starts becoming a moral one, because rarity implies value, and extreme rarity implies extreme value. This is a principle we already understand intuitively in other contexts. A painting by an unknown artist is pleasant. A painting by Vermeer is priceless, partly because there are only 34 known works in existence. A species of beetle that exists in billions is unremarkable. A species that exists in a single population on a single island is a conservation priority precisely because its loss would be irreversible. We instinctively protect what is rare because we understand that rarity and replaceability are inversely related. The rarer something is, the less likely it is to reappear if lost. Now apply that logic to a cosmic scale. If complex, intelligent, technological life is not just rare but possibly unique within our galaxy, then our civilization is not just valuable in human terms. It is valuable in universal terms. Its loss would not be a local tragedy. it would be a cosmic one. The extinction of humanity, or even the collapse of human civilization back to a pre-technological state, would not just end our story. It would end the only story of its kind within 100,000 light years. Perhaps the only story of its kind, period. This is not human arrogance dressed in scientific clothing. It is the opposite. It is the recognition that we did not earn our position. We did not choose to be the species that threaded every needle, passed every filter, survived every bottleneck. We are here because of a chain of events so improbable that taking credit for it would be like a lottery winner taking credit for the laws of probability. We are not special because we are superior. We are special because we are lucky. And luck, by its very nature, does not repeat on command. The fragility of what we have is the part of this story that should keep us awake at night. We tend to think of human civilization as robust. We have cities on every continent. We have 7 billion interconnected minds. We have nuclear power, satellite networks, and medical technologies that would have seemed miraculous a century ago. Surely a species this established, this widespread, this technologically capable, cannot simply vanish. But the rare Earth hypothesis reminds us that fragility operates on timescales we are not wired to comprehend. The conditions that produced us took 4 billion years to assemble. The civilization we have built took roughly 10,000 years from the first agricultural settlements to the present day, and the window during which we have been capable of detecting or being detected by another intelligence is barely a century old. We are a 100-year-old structure built on a 4 billion-year-old foundation, and that foundation, stable as it has been, is not guaranteed. The threats are real, and they are documented. An asteroid of sufficient size could reset the biological clock in an afternoon. The Chicxulub impactor that ended the Cretaceous period 66 million years ago was roughly 10 to 15 kilometers in diameter. It released energy equivalent to several billion nuclear weapons detonating simultaneously. It killed 75% of all species on Earth. If a similar impact occurred today, the immediate destruction would be catastrophic, but the longer-term consequences would be worse. Firestorms, impact winter, collapse of photosynthesis, disruption of the food chain. Human civilization, as currently structured, would not survive intact. And while we are developing the technology to detect and potentially deflect such objects, our capability remains limited and our funding remains modest. We are spending more money annually on coffee than on planetary defense against extinction-level impacts. Supervolcanic eruptions represent another class of threat. The eruption of the Toba supervolcano roughly 74,000 years ago may have reduced the human population to as few as a few thousand individuals. We nearly did not make it. A similar eruption today, at Yellowstone or one of the other known supervolcanic systems, would not necessarily end humanity, but it could collapse global agriculture for years and trigger a cascade of political and social breakdowns that would be extraordinarily difficult to recover from. And then there are the self-inflicted threats. Nuclear weapons, climate change, pandemics enhanced by biotechnology, artificial intelligence systems whose behavior we cannot fully predict or control. Each of these carries a probability of civilizational damage that is not negligible, and the rare Earth hypothesis adds a layer of urgency to each of them that is easy to miss. Because in a universe where complex life is common, a fallen civilization is a tragedy but not a catastrophe. The universe has others. The experiment continues elsewhere. But in a universe where complex life is vanishingly rare, every civilization that falls takes with it something that may never be replaced. The stakes are not just human, they are cosmic. Every risk we fail to mitigate is not just a gamble with our own future. It is a gamble with the only known instance of a phenomenon so improbable that the universe may have produced it exactly once. There is another dimension to this fragility, that is less dramatic but perhaps more insidious. It is the question of whether technological civilizations are inherently short-lived. The rare Earth hypothesis addresses the probability of complex life arising. But even if a civilization beats all the odds and emerges, there is no guarantee it will last. In fact, there are reasons to suspect that the very qualities that make a species capable of building technology also make it capable of destroying itself. Intelligence, curiosity, ambition, the drive to harness energy and reshape the environment, these are the traits that build civilizations. But they are also the traits that build nuclear arsenals, destabilize climates, and create technologies whose second-order effects are impossible to predict. The same cognitive abilities that allowed us to split the atom also compel us to build 10,000 warheads. The same ingenuity that gave us the internal combustion engine is altering the composition of the atmosphere on a geological timescale. It is possible, perhaps even likely, that technological civilizations face a narrow window of vulnerability shortly after they develop the power to affect their own planet on a global scale. A window where their ability to cause harm outpaces their wisdom to avoid it. If most civilizations fail to navigate that window, then the rare earth problem is compounded by a longevity problem. Not only is complex life rare, the civilizations it produces may be brief, candle flames in a cathedral of darkness, burning intensely for a moment and then guttering out. This is a sobering thought, but it is not a hopeless one, because embedded within the rare earth hypothesis is something that looks, from the right angle, like a source of fierce and determined purpose. If we are rare, then we matter, not in the sentimental greeting card sense, in the structural, load-bearing sense. If the universe has spent 13.8 billion years and trillions of planets to produce one civilization capable of understanding it, then that civilization has a responsibility that transcends politics, economics, and every other parochial concern that dominates our daily lives. The responsibility is simply this: survive. Not just for our own sake, for the sake of everything we represent. For the sake of being the only known point in the cosmos where the universe became aware of itself. This is not mysticism. It is arithmetic. If you have one copy of something irreplaceable, you protect it. You do not leave it on a bus. You do not set it next to an open flame. You do not gamble with it for short-term convenience. And yet, when we look at how our species is managing its only planet, its only biosphere, its only shot at long-term survival, gamble is a generous description. The rare earth hypothesis reframes environmentalism, space exploration, existential risk reduction, and long-term planning not as optional luxuries, but as existential imperatives. If the conditions that produced us took 4 billion years to assemble and may never be repeated, then protecting those conditions is not just good policy, it is the most important thing a civilization can do. Every species we drive to extinction is a thread pulled from a tapestry that took billions of years to weave. Every degree of warming we add to the atmosphere is a nudge toward instability in a climate system that complex life depends on. Every nuclear weapon we build is a loaded gun pointed at the only known instance of technological intelligence in the galaxy. The math is not ambiguous. The rarer we are, the more each of these actions matters. And the rare Earth hypothesis says we may be rarer than anyone wants to believe. But the hypothesis also carries something unexpected, something that, if you let it, can transform the dread of cosmic loneliness into something more like awe. Because there is another way to read the silence of the universe. Instead of hearing emptiness, you can hear significance. If 100 billion stars produce nothing in our galaxy but gas and dust and dead rock, and then one particular arrangement of matter on one particular planet, in one particular arm of the spiral managed, against all odds, to produce a species that could look up and ask why, then that is not a cause for despair. That is the most extraordinary thing that has ever happened. Not extraordinary because we say so. Extraordinary because the math says so. Extraordinary because the chain of improbabilities that produced us is so long and so fragile that the result, us, sitting here, thinking about this, is a statistical miracle in the most literal sense. Not supernatural, not magical, just so unlikely that the word ordinary will never apply. There is a concept in philosophy called the absurd, the tension between our desire for meaning and the universe's refusal to provide it. The rare earth hypothesis does not resolve this tension, but it reshapes it. Because the hypothesis does not say the universe is meaningless. It says the universe is overwhelmingly simple. It says that complexity, structure, awareness, these are not the default, they are the exception. And exceptions, by definition, are precious. The silence of the cosmos is not a denial of our significance. It is a measure of it. The quieter the universe, the louder our existence becomes. This is not a comfortable conclusion. It does not offer the warmth of knowing that cosmic neighbors share our struggles. It does not offer the excitement of imminent contact. It offers something harder and, in its own way, more profound. It offers the weight of mattering in a way that most people never have to reckon with. If we are the only minds in the galaxy, then every decision we make echoes not just through human history, but through cosmic history. Every choice to invest in science, in education, in the long-term health of our planet, in the exploration of space, is a choice to extend the reach of the only consciousness the universe has managed to produce in 13.8 billion years of trying. And every choice to ignore these things, to prioritize short-term comfort over long-term survival, is a choice to risk squandering something that the cosmos may never generate again. The rare Earth hypothesis does not close the door on wonder. It does not say the universe is boring or that our questions about life beyond Earth are pointless. It says that the answers may be different from what we hoped, and that those answers carry obligations we have barely begun to consider. It says that the search for life should continue, because every piece of data, whether it confirms our loneliness or challenges it, makes us wiser. It says that even if we find microbes on Mars or in the oceans beneath the ice of Europa, the gulf between microbial life and the kind of life that asks questions about its own existence is so vast that finding bacteria should not comfort us into complacency. It should sharpen our awareness of how improbable the next steps are. And it says one more thing, something that is easy to overlook but maybe the most important message of all. It says that the universe did not owe us this. There is no law of physics that requires consciousness. There is no equation that mandates wonder. The cosmos was under no obligation to produce a species capable of music, or mathematics, or love, or the particular bittersweet ache of looking up at the stars and wishing someone would answer. It did it anyway. Not because it was destined, not because it was designed, but because 4.5 billion years of geology, chemistry, and evolution, balanced on a knife edge of improbability, happened to converge on one unremarkable rock orbiting one unremarkable star in one unremarkable arm of one unremarkable galaxy. And the result was anything but unremarkable. You are made of atoms that were forged in the cores of stars that exploded before our sun was born. You are assembled from elements scattered across light years of space, gathered by gravity, organized by chemistry, animated by evolution, and brought to awareness by a process so unlikely that the universe may have achieved it only once. You are not a spectator. You are the payoff. You are the cosmos looking at itself. You are the silence becoming a voice. And the rare Earth hypothesis, for all its loneliness, for all its cold arithmetic, says that this voice matters more than we ever imagined. Not because someone is listening, but because no one else is speaking. So the next time you look up at the night sky and you feel that ancient human instinct to search the darkness for a sign of company, Let yourself feel the silence. Do not flinch from it. Do not fill it with hopeful assumptions or comforting fictions. Let it be what it is, vast, cold, unanswering, and then let yourself feel what comes after the silence. The slow, dawning recognition that you are standing on the surface of something extraordinary, that the ground beneath your feet is not ordinary ground. It is the product of a chain of miracles stretching back to the birth of the galaxy, that the air you are breathing is not ordinary air. It is the exhaust of billions of years of photosynthesis, shielded by a magnetic field powered by a molten iron core, on a planet steadied by an improbable moon, in an orbit maintained by the delicate gravitational ballet of a solar system that got lucky. You are the rarest thing the universe has produced, not because you are the center of creation, but because creation almost never gets this far. The rare Earth hypothesis does not diminish you. It elevates you to something almost unbearable in its significance. You are the universe's longest shot, its most improbable outcome, its single, flickering candle in an ocean of dark. Do not blow it out.